So one of the things about chemical reactions is the calculations we've been doing so far, as far as stoichiometry is concerned, is like if I ask you how many grams of A are required to react with 10 grams of B, that would be in a perfect situation where both reactants would be used up at exactly the same time. And so that's why in a lot of questions, remember last week I was saying that some of these questions say like if there's 10 grams of A and an excess amount of B, then how many grams of whatever, you know, it's like, it tells you something about excess. Okay, I'm just dropping things all over the place. And so that's what it's in reference to, because very rarely do you have a chemical reaction where both reactants are used up at exactly the same time. So we usually don't have the exact amounts. Usually in a chemical reaction, you'll have one reactant that is an excess, means there's too much of it, and the other reactants is going to be used up first. So let's say I've got a random reaction, A plus B yields C plus D. Now, if I've got 10 grams of A and 10 grams of B, chances are that A and B don't have the same molar mass, and so they're not going to be used up at exactly the same time. Okay, so it's kind of like if I want to make a cake, and if I want to make one cake, I need I'm just making up a recipe. Okay, so I need 3 eggs and 2 cups of flour. Okay, that's the standard recipe, whatever. I know there's sugar and other things, blah, blah, blah. But for this purpose, we're going to go with this. And let's say I'm given 5 eggs and 5 cups of flour. How many cakes can you make with that amount that you're given? So you would have to basically say, okay, if I've got 5 eggs and 5 cups of flour, and one cake takes 3 eggs and 2 cups of flour, I can make, after one cake, I'm going to have 2 eggs left, and I'm going to have 3 cups of flour, but I can't make a second cake with those ingredients, right? Because I need the opposite. I need 3 eggs, and I only have 2. So in this case, eggs are the limiting reactant or the limiting ingredient, because the number of eggs limits how much cake you can make. And what you're left with is an excess of flour, because you have more than enough left over. Okay. When you have that in chemistry, if one reactant is used up, then the reaction stops, because let's say B is limiting. So B runs out first and you've got excess amount of A. You can't turn A into C and D without B. So this is called the limiting reactant, because it limits the amount of products that you can make. So the reactant limits the amount of the other products that can combine and the amount of product that can form in a chemical reaction. That is called the limiting reactant. The excess reactant is the substance that is not completely used up. Excess means extra or too much. Same. So there's going to be an easy way to, one, figure out that you're dealing with a limiting reactant question. And that is when you're given the amount of reactants, for both of them, I mean, you're given the amount of both reactants. For example, in the last one where I had A plus B yield C plus D. So far, the kinds of questions you've been getting is, if I have 10 grams of A, how many grams of C can I make? Or how many grams of D can I make? Or how many grams of B are required, right? Those are the questions we've had so far. But what happens if I ask you, if I have 10 grams of A and I have 10 grams of B, how many grams of C can I make? One of these two, A or B, is going to be the limiting reactant. And so going back to the cake thing, if I only have enough ingredients to make one cake, I can't tell my customers, oh, I can make 2 cakes with that, because I can't. So it's really important in industry, especially when you're making raw materials that are going to be used in other industries, that you are able to calculate how much product you can make based on the amount of ingredients or reactants you're using in your process. So let's just consider the reaction of carbon plus oxygen yielding carbon dioxide gas. According to this equation, 1 mole of carbon reacts with 1 mole of oxygen gas to form 1 mole of carbon dioxide. Let's say you can mix 5 moles of carbon with 10 moles of oxygen. So if I have 5 moles of carbon and 10 moles of oxygen, there's more oxygen than you need, okay? Because it's 1 to 1, right? There's 1 mole of carbon that reacts with 1 mole of oxygen. If it's 5 to 10, this one's going to run out first. You're going to use up all 5 moles of carbon, and you're going to have 5 moles of oxygen left, because it's a 1 to 1 ratio. So carbon is called the limiting reactant because it limits the amount of carbon dioxide that can be formed. So if I were to give you this question, you've got 5 moles of carbon and 10 moles of oxygen, how many moles of carbon dioxide can you make? You have to use the limiting reactant amount to calculate for the amount of product, because it's going to run out first. In this example, oxygen is the excess reactant, which means if you were to calculate, let's just say I'm in the business of, I need carbon dioxide for whatever my business is. Maybe I'm like a Coca-Cola producer and I need carbon dioxide to add to my sugar water to make Coke, right? And let's say you have a carbon dioxide producing factory. And I go to you and I say, okay, if I give you 5 moles of carbon and 10 moles of oxygen, how many moles of carbon dioxide can you give me for that? And I'll pay you based on that. If you were to tell me, oh yeah, sure, I can make you 10 moles of CO2 from that, you're only going to end up making 5. And then when I come back, I'm like, well, what happened to the other 5? You said you could make 10. That's the problem if you use the excess reactant. And we'll go through a number of examples of this. So using this example, you've got 5 moles of carbon that react with 5 moles of oxygen to form 5 moles of CO2. After that, you have 0 moles of carbon left, but you have 5 moles of oxygen left. This is a limiting reactant. Oxygen is excess. So for example, silicon dioxide, which is also called quartz, is usually quite unreactive, but reacts readily with hydrogen fluoride according to the following equation. Okay, so we start with a balanced equation always. If 2 moles of HF are exposed to 4.5 moles of SiO2, which is the limiting reactant? Okay, so the first thing is, how do you know if you have a limiting reactant problem? Therefore, you have to figure out which of the reactants is limiting. Therefore, you have to use that amount to do the calculation. This is the clue. You get 2 amounts. You get the amount of both reactants. In the question so far, you've only been given 1 data point, 1 value. And then you're asked to calculate the value, like, you know, whether it's grams or moles of something else. In limiting reactant problems, you are given the amounts of both reactants. So there's a couple of ways that you can do this. You can go with the conversion factor way, or if and only if the units that you're given are the same, you can do the proportion. Okay, so let's do the the conversion way first. Now, it doesn't really matter which reactant you pick, just pick one. I'll take 2 moles of HF because it's the first one there. What you're going to do is pick one of the reactants and calculate how many moles of the other reactant you would need to react perfectly with that amount. So if I take 2 moles of HF and I calculate how many moles of SiO2 needed, and I compare that with how much I have, I can figure out if it's the limiting reactant or the excess reactant, because both of them are going to exist in every reaction. One of them has to be limiting, one of them has to be excess. So if I multiply times my mole ratio, so I've got 4 moles of HF on the bottom and 1 mole of SiO2 on the top. So I cut moles of HF and I get 2 divided by 4, which is 0.5 needed. How much do I have? I have 4.5 moles of SiO2. So the last question you ask yourself is this: do I have too much or not enough? If it's too much, then this is the excess reactant. If it's not enough, it's limiting. So that's how you want to do it, okay, for the conversion factor way. The concept is the same for the proportion way, in the fact that you pick one. So let's just go ahead and answer this question. If I need 0.5 and I have 4.5, is that too much or not enough? Anybody? And that's correct. Anybody else? I need 0.5. I have 4.5. Do I have too much or do I have too little? Nicole, yes. Anyone else? Brave, correct. Bang, correct. So all you have to do is, if I have 4.5, need 0.5. Do I have more than I need? Is 4.5 more than 0.5 or is 4.5 less than 0.5? 4.5 is more than 0.5. So I have more than I need. That is too much. So that means SiO2 is limiting, which means HF, oh, sorry. Sorry. Excess. Oh, and I can't even spell. Excess, right? Which means HF is limiting. So if I were to ask you how much of either product can be produced, you would have to use this value. Okay, so I told you I was going to do the proportion, and now I've just written all over the screen. Let me just erase all that. Give me some space. Remember, you can only use the proportion if the units are the same. Here, they're both moles. So all I have to do is, again, I can pick a reactant. This time I'll pick the other one. I'll pick SiO2 and say, okay, I have 4.5 moles of SiO2, and I'm going to put that over the mole in the balanced equation. So that's 1 mole. And I want to know how many moles of HF would I needed over, again, the mole ratio in the balanced equation. So that's 4 moles of HF. So 4 times 4.5. So quick mental math, I'm going to do 4 times 4 and then 4 times 0.5 and add those together. So 4 times 4 plus 4 times 0.5. That's how you just separate this one first and that one. So that's 16 plus 2, 18. So I need 18 moles of HF. How much do I have? I have only 2. So imagine if you have a customer that comes to you and for whatever reason they want you to produce silicon tetrafluoride for them, and your chemist uses this amount to calculate it and tells you as the CEO of your company, oh yeah, sure, if you buy 4.5 moles of SiO2, I can make like blah blah moles of silicon tetrafluoride. You would get fired because you don't know grade 10 chemistry. Okay, this is why we need limiting reactant stoichiometry problems, so that in the real world, when you are a chemist working for a company, that you can tell your boss how much raw materials they need to buy in order for you to make whatever product you're making at whatever company you work for. Oh, my neck hurts. Okay. Wow. All right, let's do more practice. Aluminum oxidizes according to the following equation. So we've got balanced equation again. Always start with a balanced equation. Powdered aluminum, 0.048 moles, is placed into a container containing 0.03 moles of O2. What is the limiting reactant? So again, we can do this 2 ways: proportion using the mole ratio, or conversion factors using mole ratio. Whichever one you're more comfortable with, either procedure is okay. It's not like math where it's like, no, you have to do it my way and only my way. I don't know if Dr. Paul's like that, but I think Chen is definitely like that next year. You can't do an alternative way. So again, you either pick 0.048 moles of Al or 0.030 moles of O2, calculate how much you would need for the other one and compare it to what you have, what you need versus what you have. So I like nice round numbers. I'm going to go for that because that looks like the math will be easy. So if I have 0.030 moles of O2, I'm going to calculate how many moles of Al needed to react perfectly. So what that means is, what you've been calculating so far is, when I calculate for this number of moles, it is if the oxygen and aluminum would run out at exactly the same time. These would be the amounts that you react together, but that's not how much they've given in the question. So I need moles of O2 on the bottom, so that's 3 moles O2 on the bottom, and Al at the top, that's 4 moles of Al, so that cuts. So 0.03 times 4 is 0.12, right? 4 times 3 is 12, and that moves it over to the decimal. And then that divided by 3 should be 0.04. Just to double check. Trying to practice my mental math. 0.12 divided by 3. Yeah, 0.04. So I need 0.04 moles of Al. How much do I have? 0.048. So I have just a little bit too much Al, which means Al is excess, and that means O2 is limiting. Okay, so O2 is the limiting reactant. So far, I'm not asking you to calculate beyond that. We're just identifying which one is the limiting reactant. Again, we have to identify limiting reactant because that will be the amount that we use, that we use to calculate anything else in the equation. Heating zinc sulfide in the presence of oxygen yields the following. So we have zinc sulfide plus oxygen yields zinc oxide plus sulfur dioxide. Okay, combustion reaction. If 1.72 moles of zinc sulfide is heated in the presence, oh, I forgot to do the proportion. I'll do it for this one. If 1.72 moles of zinc sulfide is heated in the presence of 3.04 moles of O2, which reactant will be used up? So the reactant to be used up is the limiting reactant. So this time I'll use the proportion method. So again, just pick one of the two reactants. It doesn't matter. So I'll just pick 1.72 moles of zinc sulfide. You put it on top of its mole ratio. So that's 1 mole of zinc sulfide. Is this balanced? I didn't even check. Oh, it's not. Oh, I'm bad. Okay. Balance first, because I've got 3 oxygen on this side and only 2 on the left-hand side. So there's a couple ways you can do that. You can either do 3/2 and then multiply everything times 2, or recognize that this is another way that you can do it. If you have oxygen on the left-hand side in a formula that only comes in pairs, okay? So whatever number I put in front of O, whatever number goes here, it has to be an even number. But this is by itself, which means it doesn't, like, it's never going to be an even number on the right-hand side unless I put a 2 there. Now it's an even number. So I can put a 2 in front of that, which means I need a 2 in front of that. So I've got 2 oxygen plus 4 oxygen, 2 plus 4, so that's 6 oxygen. Oops. And so I need a 3. Okay, now it's balanced. Okay, so the mole ratio that I put underneath this is 2 moles of zinc sulfide. I'm going to calculate how many moles of oxygen I need, and I put a 3 here because it's a proportion, right? So we're comparing. If 2 moles of zinc sulfide react with 3 moles of O2, but I've got 1.72 moles of zinc sulfide, how many moles of O2 would I need? So I'm just going to cross multiply. I'm going to use my calculator for that. So I've got 1.72 times 3 divided by 2, and I get 2.58 moles of O2. Oh, I can't write it. Blech. Cannot write. Needed. Just keep in mind what you're calculating here is what's needed. And I have 3.04. That is too much. That means O2 is excess, which means zinc sulfide is limiting. What would happen if I decided to choose oxygen first? Okay, because I told you it doesn't matter which reactant you choose because you will end up getting the same results anyway. So let's just say I didn't choose zinc sulfide to calculate. Let's say I chose oxygen instead. And this time I'll do the conversion factor way. So I've got 3.04 moles of O2, and I'm going to calculate moles of zinc sulfide needed to react with that. So I've got 3 moles on the bottom, 2 moles on the top, zinc sulfide. Cut that. Now, if I'm doing my mental math, I got 3 times 2 is 6, and 0.04 times 2 is 0.08, divided by 3. So that's going to be around 2. So even in this example, you can round if you want. If you're really quick with mental math, you can round because you don't need an exact number to just determine what the limiting reactant is. If I guesstimate 6.08 divided by 3 is a little bit greater than 2, but I only have 1.72. I have less than 2. So in that respect, I get the same answer. zinc sulfide is limiting. So I would use this amount to calculate for my product. Okay, use the following equation for the oxidation of aluminum in the following problems. So, which reactant is limiting? If 0.32 moles of aluminum and 0.26 moles of O2 are available. Okay, again, I can do both proportion and conversion factor method. It doesn't really matter. But just to make it easy, I like proportions. So 0.32 moles of Al over 4 from the balanced equation. And I'm going to calculate how many moles of O2 I need over 3 from the balanced equation. So X is equal to, what is that? 96, 0.96 over 4. And I don't know what that is in relation to 0.26. So 0.96 divided by 4, that's equal to 0.24 moles of O2 needed. And I have 0.26. So I have 0.02 moles of oxygen too much. So that means it's excess. Which reactant is limiting? Aluminum. Okay, now I've got another problem, which is covered up. There we go. How many moles of Al2O3 are formed from the reaction of 6.38 times 10 to the minus 3 moles of O2 and 9.15 times 10 to the minus 3 moles of Al? Okay, so now I'm given two different amounts for both reactants. I'm given new amounts from the first question. I'm going to be smart, and I'm going to recognize that both numbers are times 10 to the minus 3. And since I only need to identify which one is the limiting reactant and then use that amount, I'm going to ignore, for the purposes of just identifying the limiting reactant, I'm going to ignore the times 10 to the minus 3 until I find which one is limiting. Then I'll come back and I'll use the accurate number, okay? Because you're just trying to figure out which one is going to run out first. So if I pick, let's go with the 9.15 this time. 9.15, that's Al, over 4 equals X over 3. Okay, I hope you guys understand why I'm ignoring the times 10 to the minus 3. It is unnecessary because I'm only trying to compare this amount. So if I take 9.15 and then I compare it to 6.38, how many moles of O2 would I need? So I've got 9.15 times 3 divided by 4. Okay, got an error. Times 3 divided by 4. And I get 6.8625. So I'm comparing that to what I have. Okay, ignoring the 10 times minus 3 right now. If I need 6.8 and I have 6.3, that means that O2 is limiting. Okay, now that I've identified O2 is limiting, and now I can answer the question, how many moles of Al2O3 are formed? I use this amount. Sorry, I got very sloppy up here. I'm going to use this amount because this is the limiting reactant. 6.38 times 10 to the minus 3 moles of O2. And I'm going to calculate moles of Al2O3. So my balanced equation, 3 moles of O2, 2 moles Al2O3, cut. 6.38 times 10 to the minus 3 times 2 divided by 3. And I get 4.6 0.25 times 10 to the minus 3. Now, what happens if I ignored limiting reactant and I just picked one and I went with it? Well, let's say I chose to calculate with aluminum and just ignored the limiting part, okay? So if I calculate 9.15 times 10 to the minus 3, excuse me, moles of Al, and I'm going to calculate moles of Al2O3. So I've got 4 moles of Al, 2 moles Al2O3, cut 9.15 times 10 minus 3 times 2 divided by 4. And I get 4.58 times 10 to the minus 3. So you see, I get a larger number than my limiting reactant. So imagine it's your job as a raw materials chemist to tell your boss how much raw material to order in order to produce the yield that they want. If you use the excess reactant, you would be fired. Okay, so the answer is here, 4.25, because that just means that given, I know the board's a mess right now, but given these two amounts, the oxygen is going to run out first. And if there's no more oxygen, there's no more reaction. Okay, I'm just going to skip to the next one. Here we go. All right, now I want you to practice. So here I've got an equation. It looks like it's already balanced because I see a 2 as a coefficient. Just check the rest. Silicone, yep. Oxygen's 4, 4, yep. Okay, now I'm going to do this one because it's grams and grams. Now again, grams and grams, as long as the unit is the same, you can use a proportion. But if it's grams and grams, you need to do a little setup first. So it's the same way that we did it. It's the same way we did it last time. So you would put, I usually do it underneath the formula, put the reacting mass underneath it. So if I'm doing between ZrSiO4, I'm going to calculate the reacting mass. There's no coefficient, so that means it's one mole. So if I calculate 1 mole of ZrSiO4, oh my God, where is zirconium? Here, 91.22. I'm just going to calculate the mass. 91.22 plus silicon is, oh, I can't see. 28.09 plus 4 times 16. So that's 183.31. Now for chlorine, because that's the other reactant, I have to take into consideration that 2 moles of chlorine are part of the mole ratio. So if I do Cl2, chlorine is 35.45 times 2, I get the mass of 1 mole of Cl2, but I need 2 moles. So I multiply that times 2 and I get 141.8. So again, it's 1 mole to 2 moles. So if I do my proportion, again, I'm given the amounts of both reactants. So I'm just going to take 862 grams of SrSiO4. Who say that 3 times fast? And how many grams react according to the balanced equation? 183.31. I want to know how many grams of Cl2 I need. The reacting is 141.8 grams. So 862 times 141.8 divided by 183.31. And I get, ooh, evil number, 666.8 grams of Cl2 needed. How much do I have? I have 950. I've got way more than I need. So that means this one is limiting. And this is excess. So now knowing this, you can take this amount to calculate what mass of ZrCl4. So I'll go ahead and do the molar mass here so I can do another proportion. So zirconium, what did I say it was? 91.22 plus, and then Cl is 35.45 times 4. The reacting mass here is 233.02. So if I want to answer the question, I need to use the limiting reactant. So it's 862 grams over the reacting mass, which is 183.3. Oh, I cannot. 183.31. I'm calculating for X, reacting mass, 233.02. So 862 times 233.02 divided by 183.31